So what is omega? First thing that we want to do is connect omega with the quantity that we talked about last class, which is the period. So sort of like the most basic thing that you can say about an oscillatory motion is how much time it takes to do one complete oscillation, to come back to the initial place with the same initial velocity, right? So what's the connection between omega and the period? So we said that the position is described by this. I know that after some time t, which is the period, the particle is going to be exactly in the same place. So a cosine of omega t plus capital T plus phi 0 should be equal to the particle, to the previous location of the particle, a period t before that. So that is a cosine omega t plus phi 0. Okay, so we have a cosine of omega t plus omega period plus phi 0 equals a cosine omega t plus phi 0. Let me call the phase omega t plus phi 0. Not the initial phase, but the phase. This is initial phase, this is phase. So just to look at this in a more compact way, that will be cosine of the phase plus omega times the period should be equal to a cosine of the phase. This equation is valid for any time t, right? At any time that you choose to start your stopwatch, a period t later, the particle is going to be back there moving in the same direction, no matter where you started, right? So the a is of course the same, and you know that the function cosine or sine are periodic, and the periodicity is 2 pi, right? Cosine of any angle plus 2 pi is the same as the cosine of the angle. You just went around once, correct? So that tells you immediately that this omega times the period should be 2 pi. And therefore, the connection between the angular frequency, as it's called, the period, is 2 pi over the angular frequency. That's the period. That's the angular frequency. Did anybody notice that I'm calling this omega angular frequency instead of angular velocity? They're different things, right? Because when we're talking about an oscillator, the oscillator is not going in a circle. That was an analogy, right? That was a one-to-one correspondence between the motion of the oscillator and the motion of a particle in circular motion, right? For a particle in circular motion, I would have to call that omega, I would call it angular velocity. So just plug that in, the acceleration on the right-hand side and the position on the left-hand side. So you have minus k times the position, which is a cosine omega t plus phi 0 equals m times the acceleration, which is minus a omega squared times the cosine of omega t plus phi 0. And you see that cosine is on both sides. That's a great thing because that's a function of time. If it didn't cancel, we'd be in trouble. So this cancels with that. The amplitude also goes away, which is interesting. The minus sign cancels with the minus sign on the other side. And you get k equals m omega squared. So this educated guess about the solution being of the form a cosine omega t plus phi 0 would be a solution of the differential equation that we're talking about of f equals ma if this was true. If you pick your omega as the square root of k over m. If you do that, then that is a solution. So the angular frequency depends on the spring constant and the mass. Interestingly enough, the angular frequency is not a function, does not depend on A. So think about that. You have a spring and a mass attached to it, and then you stretch the mass a little bit and you let it go, and this thing is going to move back and forth, and you time that, and you find whatever period, 1 second for the whole oscillation, right? Now you take the same system, you stretch it 2 times as much, you let it go, start your stopwatch. It will come back here exactly 1 second later, just like this one did with this very short motion over here. You stretch it even more. In principle, you know, if the spring was ideal, you could stretch it all the way to infinity. Then you would stretch it a mile. You let it go from that 1 mile. It's going to go back to your original point 1 second later. Right? So that seems pretty weird. But that's exactly what happens. That's exactly what happens with a simple harmonic motion. The initial amplitude does not matter. You can think of it as if you stretch it more, on average you have more force acting on this system, which is making it accelerate much faster than this one. Right? So even though you cover a longer distance, you're covering that distance in a shorter amount of, with a greater velocity. You're covering the distance, greater distance with greater velocity, and that compensates exactly. So it takes the same amount of time. What's the maximum velocity that a particle in simple harmonic motion can have? What's the maximum speed, I should say speed, because not care about the direction. What's the maximum speed that it can have? If you look at the equation for the velocity, it tells you that the velocity goes up and down following a sine curve, right? And when the phase, which is omega t plus phi 0, is equal to pi over 2, for example, then the sine of pi over 2 is going to be 1, and your velocity is going to be minus a times omega. If the phase was minus pi over 2, your sine will be minus 1, and your velocity will be a omega. You know that the sine function can only go between 1 and minus 1. So that equation tells you that the maximum speed is going to be a omega, because the sine never goes beyond 1 or minus 1. So the maximum speed, it's going to be a times omega. It depends on your amplitude. If you stretch it more to begin with and you let it go, when it passes the equilibrium point, it would have more velocity than if you had stretched it less. It depends on A, right? And the point where that happens, as I just said, I'm going to draw it with a vector. What is this arrow showing? When does this happen? when the phase is equal to pi over 2, I'm talking about the speed, right? Or when the phase is minus pi over 2. Because in the first case, the sign is 1. In the other case, the sign is minus 1. So in both cases, your maximum speed is going to be this. So this describes the location of the oscillator when that occurs, when the maximum speed occurs. The oscillator will be at equilibrium, but it could be going to the left, which corresponds to this phase of pi over 2, or it could be going to the right, which corresponds to this phase. This is pi over 2, and this is minus pi over 2. So when the oscillator crosses the equilibrium point, that's when you get the maximum speed. What's the maximum acceleration in magnitude? The magnitude of the maximum acceleration. From that equation over there, you can tell what's the maximum acceleration, right? The acceleration as a function of time goes like minus a times omega squared times the cosine. The cosine maximum value can be 1 or minus 1 in magnitude. So that's going to be a omega squared. And when is that going to happen? At which points is that going to happen? When the cosine is 1 or minus 1. So when the particle is at on the uppermost right or the uppermost left. So uppermost right will be described by the circular motion particle being here. Uppermost left will be the circular motion particle being here. So that corresponds to a phase of pi, 0 or pi. This is 0, this is pi. So the phase, when that happens, is equal to either 0 or pi, maximum acceleration. Now in terms of energy, how do we describe the motion of an oscillator? What's the potential energy of a spring? 1/2 of k x squared. As I said, I'm dropping the delta x notation. So if you plot that as a function of x, where x is measured from the equilibrium point, then you have this, a parabola. If you start with some initial energy, for example, if you stretch the mass all the way to some amplitude A and you let go of it, right? You're giving the oscillator how much energy? You're giving the oscillator an amount of energy equal to 1/2 of k A squared, right? That's the initial amount of energy, the amount of money that oscillator can spend. So the oscillator starts moving this way. So some of that potential energy, initial, starts to get converted into kinetic energy, right? So the potential energy goes down, the kinetic energy goes up. When the oscillator crosses the equilibrium point, everything is in terms of kinetic, no potential energy left. It is moving to the left, so it overshoots the equilibrium point and starts to climb on the other side of the potential energy parabola, until it stops on the other side at a location minus a from the equilibrium point, right? And the total amount of energy at all times has been the same number. If you're here, you have this much kinetic energy and this much potential energy, elastic potential energy, right? I'm plotting here U of the spring. And energy conservation guarantees that no matter where you are, you will have this amount of energy, okay? Now thinking about this, we can answer the question of why is the oscillator motion so universal? Why do we describe the motion of so many different things with the same equations that we use for a mass and a spring? Now we can understand why. Any object that moves in some way, repetitive way, is going to be subject to a conservative force. because otherwise the object will be losing energy and it will eventually stop. So your potential energy doesn't have to be elastic. If you don't have a spring in your problem, then your potential energy is not elastic. It will be something else. It could be gravitational potential. If you put that marble in the video in a glass, for example, and you let it go, then the potential energy that you're talking about is gravitational potential energy, right? If you are talking about the motion of an atom as part of its molecule, then your potential energy will be something else. It will have a particular shape, right? But whatever your potential energy function, whatever shape it has, it probably will have some points that it will probably have minima and maxima, unless it's completely flat. If it's flat, then it's not that interesting. Very few things in nature will have that potential energy like that. Gravitational is one of them, but not much more than that. So it would probably have some sort of minima, right? And at this point, at the minima, here and here, you can describe the potential energy function as a parabola. If you're taking calculus, we're talking about a Taylor expansion of any function. The potential energy as a function of position, you can approximate it. You can approximate it by saying it has some value. At this point, it has some value. If it's a minimum, the slope is 0, so I don't have to worry about a term that has to do with the first derivative. There's a 0 there. The next term in this Taylor expansion, if you haven't covered that, that's okay. The next term has to do with the second derivative of the function with respect to position. And that goes with the delta x squared. This second term, this is a constant evaluated at whatever point you're talking about. So let's say that this is x0. So that second derivative is evaluated at x0. It has some value, and the potential around that point behaves, it can be approximated as a parabola. If you don't move too far away from the minimum, if you're close to the minimum, a parabola does a very good job in describing that potential. Okay? The Taylor expansion of any function will have second derivative, it will have third derivative, and so on. But the dominant term, of course, will be this one if you're near the equilibrium, because the first derivative, the slope is 0 at a minimum. The initial value of the potential energy has never been important, right? There's no physics associated with where you set your energy level, your level for the reference level for the potential energy. That's always been unimportant. So you can just set this equal to 0, and you see that any potential energy function can be approximated. This should be in half here, right? Can be approximated as 1/2 of the second derivative of the function, evaluated at the minimum, times the displacement from the equilibrium position squared. So everything can be approximated by a parabola near the minimum point. So it is that universality, which is coming from the math of functions and the Taylor expansion of any function, that tells you that if you have an object that is oscillating back and forth around an equilibrium point, if the oscillations are not too wide, right, then that motion, it's going to be very well approximated by a harmonic oscillator motion, which has this feature, right? This is 1/2, and your effective K for that motion, your K effective, will be the second derivative of the potential energy function evaluated at the minimum point. Okay? This is just to explain to you why this is so broadly applicable to oscillatory motion in general. So the equation that we started with this class was this. And that was the equation for a mass attached to a spring. That equation can also describe the motion of, say, a pendulum. But the location of the position of the pendulum, for example, you don't have to, it doesn't always have to be the x position. In fact, if you think about the blue board that I had some classes ago and I let it oscillate about some pivot point, right? You will describe that oscillatory motion not by saying what's the x location of some point in it. You will describe it by saying how does the angle change with time. Okay? So what I'm trying to say is that the equation for simple harmonic motion doesn't have to always have an x there. It could be some other variable. Right? So in general, it's going to be a function, an equation that has some constant here multiplying some variable. I'm going to call it z, that can stand for x, y, angle, deflection, anything. If that physical quantity that I'm calling z satisfies this equation, that when you take the second derivative of that quantity as a function of time, you multiply by a constant, is equal to the quantity minus sign, with C1 and C2 being positive. That's important here. Then you know exactly how to solve that equation, right? I already told you what the solution of this equation is, so you know what the solution of a general equation like this is. It's the same equation, you're just changing how you call the variables, right? So the solution of this is z as a function of time is equal to some amplitude times the cosine of omega, right, times t plus some initial phase. And omega has to satisfy this. To be a solution, omega has to satisfy this. But of course, we don't have k and m in a general equation like this. So it's going to be the square root of C1 divided by C2. So whenever in your studies, chemistry, whatever you're taking, biology, population of some animal, how does the population, the number of animals change with time and so on, if z stands for population, and you see an equation that says that the second derivative of the population multiplied by a constant should be equal to some negative number times the population, you know that that population is going to behave like this. Right? That species is going to oscillate back and forth between some maximum population and some minimum, maximum and minimum. And that is the solution.